The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. We'll just start in a minute. About 2, we'll actually carry on with this. Welcome to the Spark Circle webinar. Today we'll actually be doing to derate or not to derate. That's actually the topic today. My name is Sajjan Baldu. I'm the regional steam expert for the central region here. I also have Mark, who will join in and do some questions after as well. But he's on the call too, will help me out with the questions towards the end. If you have any questions, you'll be muted. So Mark's up there as well. But in the question section on your right, do put your questions down in and we'll answer them towards the end of the presentation as well. Well, we're talking about derators today. It'll be a shorter presentation. It might not take the whole hour, but we'll go through it, and if you have any questions, we'll obviously get to those as well. So typically on all steam systems, there's a need for the boilers to be fed with water so that you can make this steam. And the pre-treatment of this feed water becomes one of the most important function in any of them as well. The reasons for them, the reason for the pre-treatment, to begin with, on an energy perspective, you would want, if you put cold water into a boiling pot of water, it actually kills the boil. So one biggest thing is to have the temperature up, high up, so that it doesn't kill the boil that's actually already going on in the boiler. So that's one of the basic ones, but the other ones as well, as you go through it, for the boiler, those boilers are now made of stainless steel. They're susceptible for corrosion. So you would want to remove oxygen and any non-condensable gases if you can, bring it down to minimal amounts. Oxygen, yeah, you would want to remove it completely. That's the whole idea behind it. Then heating up of the feed water. So if you have hot feed water going into a boiler, that's actually when you would actually make sure that you don't kill the boil. You're actually generating, the boiler still keeps on going as well. So having the temperature. The other benefit of heating up the water we'll talk about is it gets rid of the non-condensable gases, which is air, which is in the water itself. Then after you've done this function of removing oxygen, heating up the water, you would want to store this in that above condition, so that after you've made this happen, you don't want the temperature to go down or more air to come get into the feed water either. Let's talk about oxygen in water. And we know there is air in the water, there's oxygen in the water because it sustains life, marine life. There's significant amount of oxygen. Well, not significant enough for us, but significant enough for sustaining marine life. There's different temperatures and different pressures. You'll see different amounts of oxygen content. Typically for deaeration purposes, I mean, you could do ppm, but deaeration purposes we do ppb, which is parts per billion. It's like very you're looking at very low numbers as well. So you can look at this one up here at varying temperatures. You can actually see how the ppm of oxygen will change. So the lower it is, the higher the content of oxygen. The lower the temperature, the higher. So oxygen in water is directly proportional to the temperature itself. So if you're looking at heating up the water, that's when you can actually get rid of oxygen, because it's basically directly correlated to what the temperature of the water is. So the higher it goes, as you can see, if it goes to 100 C, it goes to 0, because if you're boiling the water, you're getting rid of air at the same time as well. But in the deaerator, you're not technically boiling the water, but we'll get to that as well. You're boiling the water in the boiler. If you didn't get rid of oxygen before it goes into the boiler, when you're boiling the water to make steam, you're getting rid of oxygen in the boiler, and the oxygen can be pretty bad, and we'll show some Just so that you understand how much oxygen we're talking about, the city water would have up to 10 to 15 parts per million of dissolved oxygen. And the deaerator must reduce it from 15 parts per million to 7 parts per billion. So it's a significant, and it has to happen in a matter of seconds. As cold water comes in, it has to heat it up, remove the oxygen, and that reduction goes down to about 3,000 times of what it was in there. If you look at why it becomes important as well, if you see oxygen corrosion pictures here, it can be pretty devastating on the boiler itself. Boilers or boiler systems with very poor deaerators or very poor oxygen removing capabilities will actually have high corrosion. The tubes will corrode, or the coils will corrode depending on what sort of boiler you have, and they will have to replace, patch them up. So you're putting in a lot of maintenance into that at that point. You can also see the ones below, the picture with the two sparge tubes, and you can see what the new sparge tube looks like and what one of the really corroded sparge tubes looks like as well. And that is actually sitting in a feed water tank. Most of the time it's sitting in most likely a feed water tank. And you can see feed water tank does have oxygen and it will eat those away. Most of the time, that's why sparge tubes or any steam injectors are all made of stainless steel. Okay. Actually, one other thing, if we don't have a deaerator, because some of you might not have a deaerator, but you still be like, my boiler is not doing that, we're not having that kind of issues, we don't have corrosion issues. That's because if you're not doing mechanical deaeration, the other method they use is chemical deaeration, chemical oxygen scavenging. You're not doing deaeration, but you're just getting rid of oxygen, which is the main culprit in the corrosion. So what you're actually trying to do at that point, you add sulfites into it, and the sulfites react with the oxygen in the water, and they pull the oxygen out, which means you're spending money on chemicals, you're adding more impurities, because chemicals, even if they're not, even if they dissolve in it, there's dissolved impurities in the water. So they'll bring up the TDS conductivity, so the total dissolved solids might go up. So your flow down might be higher. We'll talk about that too. But if you're not doing mechanical deaeration to get rid of air, and along with air, oxygen in that same aspect, if you're not doing that, you're actually getting rid of it by adding chemicals, which is sulfites, which your water treatment provider will be actually adding to it. So if you look at the costs, this one is for about a 600 horsepower system where there's 80% return that's coming back. So you're just using about 20% of makeup. But in this case, you can actually see if it's the amount of sulfite calculation, the oxygen scavenger. The chemical cost for that is about $33,000 a year. That's basically what that is. If you're looking with a deaerator, because in this case, you could actually, in this case with the chemical costs, you can see the feed water temperature, which is up here in the calculation at the bottom table, is 190 F. So that's what the temperature is at that point. At 190 F, the oxygen cc per liter is like 2 cc per liter. So we're looking at it's not a lot of oxygen, but it still makes a significant effect in the deaerator, so in the boiler, so they want to get rid of it. So they add chemicals to get rid of it, and you can see the cost just to get rid of that little amount of oxygen is about $33,000 per year. If you start deaerating this, because the deaerator will bring it down to 0.007 cc per liter. So if it does bring it down to that low oxygen content, the amount of sulfites, because you would not have a deaerator which could bring it down to 0, but you would significantly reduce the amount of sulfite, sodium sulfite here, which is oxygen scavenging that you need to add to this. So it'll bring it down to $1,600. So you can see the difference that you see in the chemical costs that are significant if you don't have a deaerator as well. It also depends on if you have 100% makeup, it goes up. If you don't have much condensate coming back, it goes up as well. So it depends on how often you run. So you'll have a couple of variations to see where that stands. But just to give you guys an example, this would be one. The other issue with having, apart from oxygen being corrosive, is having air in the system itself. When you have air in the system, air is a really good insulator. As you can see from the values for thermal conductivity on the right over there, thermal conductivity of air is very low, so it makes a really good insulator. And you can see for copper, it's significantly higher because it's a really good insulator. So if you have air in the system, it starts in a steam system. Most of the time we're making steam is for heat transfer. You're trying to make sure you generate steam so that you can transfer that heat to your process or heating application, whatever it is. But if you have air in the system, then it starts also acting like an insulator, so it'll drop some of the temperature and the heat transfer capability as well in the heat exchangers. So you would want to avoid air in the system. So that's basically one of the other reasons why you would want to deaerate, because deaeration not only removes oxygen, but it just deaerates air. It's also getting rid of air as well, to an extent. And in a chemical oxygen scavenger, it's only reacting with oxygen. It's not doing anything else with any of the other. And even with oxygen corrosion, you could get pitting. You could also get, on the condensate side, you could also get carbonic acid that's also formed. Okay? So why deaerate? It improves operation of the boiler because you're elevating your feed water temperatures. So it improves that you don't kill the boil in the boiler. It avoids corrosion, as we talked about, because oxygen is the main culprit in that. It improves heat transfer, as we talked about. Steam temperatures are higher without non-condensable gases in it, like air. There's energy savings because deaerators have pressurized systems. They can be pressurized to about 5, 7. I've seen 10. In some cases, some odd cases, maybe up to 30, depending on what the system is. But now you can put high pressure condensate right back into your deaerator, depending on how much as well. So that needs to be carefully calculated, but that way you don't have any flash loss. So you could actually have some bit of energy savings in there as well. Then you can also reduce blowdown. The lower the chemical, every boiler will have a blowdown. The lower the chemical consumption, the lower the chemicals that you put into your water that's making steam, the lower the blowdown in the boiler, because you're not adding more impurities into it. So the blowdown goes down, that helps on energy savings as well, because you're not wasting, because typically blowdown goes to drain. Ways of recovering it, but if you don't do it, then obviously if you do less of it, it's good, right? So, and you reduce costs by reducing chemical costs, and you improve the equipment life by not having them corroding. A typical, how do you know if, let's say you have a deaerator, how do you know if it's even doing what it should be doing? And this is something most people miss, just even if they have a deaerator. The chemical treatment people might just be adding more sulfites to accommodate for a low performing deaerator. So the question to ask is to do a DA performance test. What you would do is, like you could see on the left, the gentleman's actually using a vacuum vial. So he breaks the vacuum ampule, it's a little ampule. He breaks it underwater, which is coming from the deaerator itself. So he'll take a sample of that so that he doesn't have external oxygen getting into it or air getting into it. And that's how he takes that sample and tests it out. So they start with a 0 to 12 ppm test kit. It should technically show 0. If it's in a deaerator, if you're getting the values there, then your deaerator is worse than any tank. Then you test with a 0 to 180 ppb test kit. They'll get a range like 5 to 20 is where it will be. A good deaerator, that's where it should be. I've seen deaerators which even go up to 50, so that would not be a good deaerator. Then you would test it with a 0 to 40 ppb test kit, and you would see the actual low values. So these are actually real results. of deaerators, because whenever we actually supply deaerators, we get them tested as well, just to make sure they're performing as they should. This is without any addition of chemicals. This is prior to adding any chemicals, these are the results. Let's talk about the requirements for good mechanical deaeration. Like, this was done by the APMA, which is the American Boiler Manufacturing Association. These are requirements that are very common. People know it. It's not like the deaerator is something new, but people have started skimping out on these designs. So we'll talk about what the design requirements are for these. Temperature, as we talked about it, temperature is in direct correlation with how much oxygen the water has or not. So temperature has to be up there. You have to be able to get the temperature high enough such that it removes the air from that from the water that's coming in. Then you need to have turbulence. So if you have a nice little laminar flow, you won't be. If it's way too uniform, then it doesn't actually agitate the air. So the more turbulent it is, the air will escape out. If you're very laminar, even if you heat it up, the air might still travel with the laminar flow. So if it's more turbulent, you can actually get some proper separation between the water that you heated and the air that's coming out of it as well. A thin film. If you don't have a thin film, if you imagine heating up a blob of water, the bigger the blob of water, the difficult it is to get uniform temperature. The outside will heat first, and the inside might not heat high enough. So you would want to maintain a thin film, or even really tiny, breaking down this water so that it heats up uniformly throughout. So if you don't have that, then you have a problem as well. So you won't be effectively heating the water properly. You won't be uniformly heated throughout. Then you have time. For heating up the water, it takes time. Unfortunately, it's not like turning on a switch. So the minute the water starts coming into the deaerator, you need to give it time for it to heat up. That's basically what that means, because if you're heating, even if you're heating any sort of water, it takes some time for it to reach temperature, right? So, and then after you've done all this, you've heated it up, you've made it thin film, you've made it turbulent, you need to vent it out. You need to make sure there's effective venting of air out of that deaerator. If you remove the air and it's still sitting in the deaerator, then it's not doing any benefit either. So, and after you've got rid of the air, you got the temperature up, you want to maintain the steady state. Maintaining the steady state is the last step, but you want to keep that temperature up. You want to make sure no other air gets into the system. So that's basically what that last step is. So I'll quickly talk about some deaerators that you'll see. A spray type deaerator like this one here, the feed water, the boiler water comes up at the top here, and all it does is you have steam coming in at the right. It goes into these like sparge tube throughout the tank, and it heats up the water and it pressurizes. But the problem with these is there's not enough time while the boiler feed water is coming in for it to ensure that it's heated properly by the time it hits the body of water. There won't be uniform heating throughout the body of water as well. You could maintain this at pressure, but these, if you have one, get it tested, because we've tested a bunch of these and a bunch of the spray type deaerators, and you'll see very low results. Like the performance is very poor. They've gone up to 50 ppb. Some are as high as 200 ppb. If they're really bad and not properly designed, they could go even higher. So the problem with this is when we saw the APMA requirements, the temperature is reached only after it fills into that piece of the body of water. The turbulence, there's no turbulence. It just comes into the body of water, and that's where it ends up. Thin film, there's no thin film. It could be a blob of water. Based on what sort of nozzle design they have, it might not even be thin enough for it to be uniformly heated. Then the time, there's barely any time by the time it hits the body of water. So you're not exactly deaerating at that point. You're deaerating in the body of water. You're trying to deaerate rather in the body of water. Then the other ones for venting. Even if you can get rid of air, it has to reach that air vent, which is in the middle. So you could have different air vents in different locations, but if you have pockets where it sits, you can't really get rid of it either. And then you may try to maintain the steady state in there. So the other type you'll see is a tray type deaerator, where in this one, you have turbulence because the tray sections create turbulence. You have temperature because you're heating it up and you maintain that as well. And you have the time that comes down through it. And the venting, everything gets up to the top and vents through the top. So air gets pushed to the top dome. So you have a good area for that air to collect at. So, and also you have a thin film because as you're falling down these trays, you actually get a nice little thin film as well. And you're maintaining then the storage section. If you just see a tank, so the deaeration only happens in this head at the top. If you just see a tank, it's basically a storage section. So it's just doing the steady state at that point. Then there is a dynamic column deaerator. This is typically on the upper end of the design because this guarantees performance. This one actually, and also it has a bunch of design features which are good for maintenance as well. First, to begin with, there's two valves. There's two different parameters that it actually measures. Instead of just doing, normally all deaerators, they just maintain pressure and that's about it. But this one maintains pressure and temperature because there's two phase, right? There's a little bit of steam in the deaerator and there's a body of water. So you want to maintain both and control them separately because you can't control one parameter and assume that the other parameter is controlled as well because it will fluctuate significantly over time. If it's a really steady flow, maybe, but even then it's not a guarantee. Then this dynamic column, instead of having trays, it's a packed column which has the metal clippings in it. So instead of having trays, it has that sort of metal clippings. So it actually allows the same time, same turbulence, and also the same thin film to happen in there. So that gives you a benefit over trays because I'll show you a picture of trays dislodging as well. So you don't have that sort of issues. And also on the water, it's typically a standard nozzle. It's not a spring-loaded nozzle, which is also an issue because if you have a spring-loaded nozzle, you might have issues of it failing as well. So this is just a standard nozzle, which is there's barely any risk of anything failing there. So, okay. And you can see on the top, you see a vent condenser up here. This is basically when you're venting air, you also vent a little bit of steam. So the deaerators vent a tiny bit of steam. So this vent condenser captures that steam. You preheat your makeup water going into it. So it's a little more efficient the way to deaerate it on a deaerator if you have a vent condenser on top of it. So it's an exhaust vent condenser where you can preheat the makeup water coming in with that. You could see one same on the vent condenser here. You can see an installation up here as well of a vent condenser, what it looks like. So as I said, it's taking the heat from the vent line on the deaerator, which typically also has a little bit of steam in it. And you use that to heat up makeup water. So looking at some of the design considerations, ask for the performance, ask for the 7 ppb or less of oxygen. I've seen people do specifications where they've said there is a clawback or a penalty, a monetary penalty if the performance is not achieved on tests after the installation is done. So there's some engineers who have specified it that way as well, where that will guarantee whoever's supplying you with the deaerator also meets that as well. Have dual control valves. If you're trying to maintain temperature with just maintaining pressure, I know it's a steam system, but it's not just a steam pipe. It's actually a two-phase flow in here. You have water, then you also have a bit of steam space at the top. So controlling two different pressure, two different parameters, pressure and temperature, with one valve, not really effective. So you'll have a lot of swings in it, which affects the performance. Having two dual control valves helps ensure that the performance is there and you're also maintaining them. And monitor these. Have something, normally they put mechanical valves. There's barely any monitoring that's done on it as well. And the best case scenario I've seen is they monitor pressure. That's about it. But to monitor pressure and temperature and level. So this will give you, if it falls off, what it should stay at. If it falls off the thresholds, some deaerators go under vacuum because they were undersized. So you don't want that happening. And if you don't notice that's happening, then it could cause a significant amount of problems, not just with oxygen. It could cavitate your pumps. You could have other issues on the pumps because the pumps don't have the NPSH on it. So there's a significant other issues that could happen as well. And maintenance items, as I said, try not to use the tray design. You use the pack column or dynamic column design, where the trays don't get dislodged. You don't have that sort of maintenance issue. Also, in spring-loaded nozzle, not recommended because there's a spring in it, so the nozzle can actually also it'll fail over time. So if you see, that's actually where one of the pictures where the trays have dislodged, and now someone has to cut it open and put them back together, right? So you don't want that happening. The other way of some people doing it, people will weld the trays, but it's a very time-consuming, expensive process. So the best one is to actually have packing, like in the dynamic column. Also, that's the spring-loaded nozzle. So you can see there's a spring in it, so there's issues with it actually jamming up as well. So you can see a DA. This is a DA in production, and you can see this one, I believe, was a 33,000 horsepower DA, and you can see two heads on top. There's a different, unique design. There's also others where it's a single head for higher horsepower boilers as well. So one DA installation, which is actually outdoor, and this was actually done outdoor as well. So technically you can, as long as you're ensuring that everything's protected from the freezing, you've taken that into consideration, you can technically be outdoor as well. So the monitor and trending, and as I said, you would want to monitor these. You would want to monitor the level, you want to monitor the pressure and the temperature. So as long as you're monitoring this, you know where it ends up, or where you're having issues, where you're having fluctuations on these as well. So monitoring these three parameters becomes really crucial for a DA performance. Even if you're not testing it based on these, you can tell the DA is doing what it should be doing or not. And I would say get it tested once in a while at least to make sure that you're actually getting the deaeration and oxygen is getting removed and you're not spending too much money on chemicals itself and wasting energy in the processes too. So, okay, that was a shorter presentation, but we're just covering the deaerator. If you guys have any, we'll get to questions. If you want to reach out to us, please reach out to us as well. If you have any other questions or if you want to run something by us. Okay, we'll get to the questions.
Yeah, so John, there was a couple questions people had when registering.
Okay.
And, so one of them is, what's the feasibility of a deaerator versus a vented feed tank?
Yeah, go on, Mark.
Yeah, it's like there's a lot of variables involved, so it'll be more, payback will be higher based on higher pressures, higher makeup water. So if you're using a lot of fresh water, then a deaerator would make sense to achieve all those things you talked about in terms of boiler efficiencies. And process implications is another one. If you're not deaerating properly, how does that air in your system affect your processes in terms of shelf life or the corrosion and rust? And anything you want to add to that one about the feasibility?
I've actually seen, maybe I'm looking at it another way as well, and seeing if someone's asking, should I go with this or that? There are some instances like low horsepower instances where the DA might not make sense monetary wise. I mean, it makes sense in a design perspective, but if when you look at the funding, you're like, oh, wait, I'm spending just as much money on the deaerator as I am on the boiler. Obviously not, right? So if you're looking at really low horsepower, that might not be something you would people would want to invest in. But if you're looking at higher horsepower, I would say anything over 200, it's something to look at. But if you also have high makeup water, like you're not returning condensate for whatever process reason, I think that would make also a good sense. You could always check with, I think, chemical costs, right? You could ask the chemical guy how much you're spending on your oxygen scavengers. That will give you an idea if your deaerator is going to be worth it or not right there. So.
Yeah, I agree. So another question is, would a deaerator improve the water for steam injected into humidifiers? So this one, my comment would be the deaerator would use less chemicals that would be entered, like going into humidification, which is important, but it won't eliminate. So you still will require some chemicals. So if the concern is about chemicals going in humidifiers, then the clean steam generator would be required to eliminate all the chemicals.
Yeah, I'll agree. If the humidification, I mean, it definitely helps, as you said, Mark. But the clean steam generator will be a better suited application if you're trying to control your steam quality going into humidification.
Yeah. Someone asked about a recommended plume length on a DA vent. I'm not an expert in this area, but I believe it's 18 inches. So probably 12 to 18 inches. I know people could be exhausting too much steam. So if you have a 4-foot plume, it's probably too much. So what I've read is about 18 inches.
Yeah, I think I'll agree with the same. Yeah, 12 to 18 inches.
And who does oxygen testing, and how frequently should we test our DA? So in this question, in terms of frequency, I would say yearly is probably a good idea. You could give your opinion on that, but water treatment professionals would be the ones to test the DA. I find a lot of boiler plants start up a DA and they never check to see if it works. They just keep adding chemicals and assume it's working. So testing it yearly is my recommendation.
Yeah, yearly, and ask who are supplying your chemicals. I mean, they might have a vested interest in it, but they will definitely do the test on the deaerator itself. So.
And the last one, unless some more come in. No, the last one was occasionally we see our deaerator go into vacuum. Can you explain why? So if a deaerator is going into vacuum, it means that that pressure control valve is not keeping up. So the steam supply to the deaerator is either undersized, or there's an issue with it, or overall the deaerator is not designed to meet the requirements. Maybe the makeup rate has changed, and that's a big benefit of having the trending, is to see if there are changes. Then what do you see? And you'll see that the pressure drop within the DA. Anything to add there?
Yeah, no, I think someone's either undersized it. I mean, if it's only happening now, maybe your pressure's gone down before the pressure valve, or you've started using more makeup water for some reason, or the plant capacity has gone up, whatever it is, right? So you're using more, or condensate's not coming back. A bunch of different reasons as well, but definitely that would mean look at the boiler, look at the DA as well.
And I guess a point of there is, if the DA is going into vacuum, then it's not deaerating anymore. It's pulling oxygen back into the DA, and you're going to end up with the corrosion issues if the chemicals aren't keeping up.
Yeah, and I've seen boiler pumps having an issue because they just cavitate, because now it used to be 5 psi on the suction, now it's like under vacuum, so they just start to cavitate.
Yeah, good point. And
but
trending is good, but and I've seen where people have changed the deaerator to a stainless steel tank, but the corrosion's just going to take place further downstream. So now it can't corrode out the tank. It'll look for the steel next in line.
Yes, I've seen people change deaerators to stainless steel, or even feed tanks. If they're corroding, they'll be like, I want a stainless steel feed tank. But the boiler's not stainless steel, so the next thing that will corrode will be the boiler. So the boiler will corrode at that point. So.
Yeah.
Okay.
Yeah, that's it, John. Thank you.
Okay, awesome. Thank you, everyone. Thanks for attending.